Hello and welcome to Unit 5, Lecture B. We're going to start talking about electrons today. And the electrons are probably the most important part of an atom as far as chemistry is concerned because the electrons are the part that are involved in chemical reactions. So electrons are going to be a two-part lecture. So part 1 today, we're just going to talk about what they are and what the different models were used to kind of explain where the electrons are, and some of them still have their purposes and we kind of use them even though they're not exactly perfect. All right, so first, electrons, really, really tiny. They're 1/1836 the mass of a proton. 1/1836 of an atomic mass unit. That's the mass of an electron. So we basically say that they have a mass of 0 because we would never have this many electrons on any one single atom for it to make any difference. So significant figure-wise, the electrons just don't count towards the mass. They have a negative charge, which is going to help us keep our atom neutral. Remember, if they use the term atom, it means that it's neutral, so it has no charge at all. If the neutrons are neutral and have no charge, but the protons are positive, making our nucleus positive, we have to have negative electrons to balance that out. So because the atom is neutral altogether, the number of electrons has to equal the number of protons. They're found in regions called orbitals. Electrons orbiting in regions called orbitals. So they're not fixed paths. They're not like the orbits of the planet where they always follow the same path all of the time. They are three-dimensional regions. They're areas or space that the electrons can be in. There's a probability that they're going to be within a certain three-dimensional shape, kind of like balloons most of the time, but they could be in other places, which is going to let them be involved in different types of chemical reactions. Ions are going to be particles that have fewer or more electrons than their neutral atoms. So we said atoms were neutral. If I have a lithium atom, the first thing I need to know how many protons and neutrons there are is its atomic number and mass, so we need the periodic table. So we've already said that the atomic number down here tells you the number of protons. So for lithium, that's 3. And the mass, we're going to round to a whole number. So lithium's rounds to 7. So lithium has an atomic number of 3 and a mass of 7, which means it has 3 protons. And if this is a neutral atom, he's going to also have 3 electrons because plus 3 and minus 3 add up to 0. And we're great. Neutrons, he has 4 because we subtracted the 2 numbers. Now, if we're going to look at his ion here where it's plus 1, atomic number is still 3, mass number is still 7. He still has 3 protons, and he still has 4 neutrons. But I have to end up with a total of plus 1. So plus 3 plus what negative number is going to give us plus 1? And so the answer is, of course, 2. So he has 2 electrons. The other way you can think about it is if it's a positive ion, it has that many fewer electrons. Positive ions have fewer electrons than protons. Let's take a look at chlorine over here as a negative ion. So again, we go back to our periodic table. Chlorine is element number 17, and we're going to round his mass to 35. So he has 17 protons. In our neutral atom, he has to have 17 electrons. And then, of course, we subtract the 2 numbers to get 18 neutrons. In our negative ion, I know the negative's small, but that's a little negative sign there for -1. He still has to have 17 protons, because if he doesn't have 17 protons, he is not chlorine. He's still going to have 18 neutrons because his mass hasn't changed. But what number plus a positive 17, what negative number is going to give us a -1? So positive 17 plus a negative 18 is going to give us -1. And again, we can think of it like we did over here. Positive ions have fewer electrons, negative ions have more electrons. So if he has a -1, he has one more electron than he does protons. Over the years, scientists have used different models to try to explain the movement and the existence of the electrons. And so we're going to talk about those briefly. You're supposed to have a brief knowledge of them. First one being J.J. Thomas's plum pudding model. I prefer to call it the chocolate chip muffin model because chocolate chips are way better than plums. Basically, they could smash atoms apart. So they knew there was some part of it that was positive and some part of it that was negative. So J.J. Thomson's model was, at the time, they thought atoms were solid spheres, that all that was there was one solid type of material. So he thought each element had its own unique solid material that was positively charged, and embedded within each of these special positive materials were negative electrons. And this would explain why the whole thing was neutral, why they acted like solid spheres, and why the negative parts that they kicked out were exactly the same no matter which element they used, but the positive stuff that would be left over was different. So Rutherford, we already talked about with his gold foil experiment. If you go back to lecture A, he shot radioactive particles at his gold foil, and most of the particles went straight through. So, of course, Rutherford then said that the atoms were mostly empty space with a dense nucleus, and the dense nucleus was different for each element, and the amount of negative charge was different, but that they were zipping around the outside, making it act like it was a solid sphere. So this kind of always looks to me like the Jimmy Neutron, that nuclear, back in the nuclear age, atomic symbol that they always used. That was kind of Rutherford's model. And he just said the electrons were zipping around there randomly in these looped paths, making it act like a solid sphere. Well, then we have Niels Bohr, and I'm going to switch models. These are the models that are in your notes, and they work just fine, but they're not as big, and I found slightly better models to show you here. So here's Rutherford's model, where you have this dense nucleus down here in the middle. Nucleus. Remember that the nucleus was made of protons and neutrons, and therefore always has a positive charge. And he had these clouds of electrons out here that are negative charge. So we have all these negative electrons orbiting, positive center, negative outside, neutral atom. It worked great. Niels Bohr, though, started working with those negative electrons and noticed that they all didn't have the same amount of energy, that some of them had more energy than the others. And because we have these opposite charges and opposite charges attract, the faster you're moving, the more energy you have, the farther away from the nucleus you can get. So these guys are all getting, of course, pulled in towards the nucleus at the same time they're moving straight out. So they're moving in straight tangent lines and getting pulled towards the middle. So kind of like centripetal force, it's making these circular-ish paths is what Bohr had. He had these perfect circles. And depending on the spectral line that they gave off, which we're going to talk about in a minute today, it'll be the last topic. They gave off different amounts of energy that he could see as light, if you remember from 8th grade playing with prisms and light and looking at light patterns. They gave off different types of light and different colors, and so he put them in these different orders. And so he called these principal energy levels. Principal energy levels, which I will abbreviate PL from now on because I don't like to write the whole thing over and over again. So the principal energy levels, and they were numbered. The closest to the nucleus would be the first, then the second, then the third as you go out. Now this model, of course, with the way we've cut it, and it's a two-dimensional model, and this is the kind of Bohr model that you made in 8th grade. They look like hoops. They look like rings, but they're not really two-dimensional rings. You're talking a three-dimensional space. So it really is more like this, where it's kind of like layers on a gobstopper. So here's your nucleus, And here's your first principal energy level or shell where the electrons can be. Here's the second, and here's the third. Okay, if you look at your periodic table, so please take out your periodic table, and you look at the period number, one of the reasons the table is set up the way it is because of those principal energy levels. Hydrogen and helium have one principal energy level there in the first period. Lithium through neon have two principal energy levels there in the second period. Sodium's in the third period. Guess how many principal energy levels he has? Yeah, 3. Okay, look at their electron configurations. So down here, underneath the atomic number, they tell you the electron configuration. Hydrogen's is just one number. Helium's is only 2. They have just one number. They have one principal energy level, one number. Lithium has 2 numbers, 2-1. Beryllium, 2-2. Boron, 2-3. All the way to neon with 2-8. All of these have 2 numbers. They have 2 principal energy levels. What these electron configurations are telling you is how many electrons are in each principal energy level. So if I look at carbon's, he has 2 electrons in the first principal energy level and 4 electrons in the second principal energy level. So it tells you where the electrons are and how they're arranged. And there were maximum numbers. The size of these principal energy levels, they get bigger as you go out, and electrons all being negative and like charges repel, you can only put so many of them close together and you run out of room. They would push each other. So there are maximum numbers. The first principal energy level holds a maximum of 2. The second holds a maximum of 8. The third holds a maximum of 18. And we'll talk more about that in the next lecture. All right, this model worked really well, but it's an oversimplification. It didn't explain all of the energy changes. It explained them fine for some of the smaller elements, but once the elements got larger, it didn't really explain it very well. So now we have this electron cloud model. Not only do we have principal energy levels, we also have sublevels within the principal energy levels. And these electrons can move from one principal energy level to the other, from one sublevel to the other. And this is just probability of where they're going to be. And if you were to take a snapshot, so this is the electron cloud model, or sometimes called the wave mechanical model. It says that there is a mathematical probability that the electrons are going to be within a certain region more of the time than they are in other regions. It's a lot more physics to explain this model, to truly understand what the electrons are really doing. This model, this simplification, tends to be the one that we use to explain chemical reactions. Okay, but they want you to know what the real model looks like. Okay, so in our lecture notes, we have that. We have our J.J. Thomson's. We learned that atoms are most empty space. We have Rutherford's model. Rutherford's model was too simplified because we knew electrons had different amounts of energy, so Bohr put them in principal energy levels. And then Bohr's model, also oversimplification, didn't explain all of the movements. So the newest model is this electron cloud or wave mechanical models, where we're talking about areas of probability, and you really have to use an X-ray and time-lapse photography to get any kind of idea of what the shapes of the clouds are. See, these clouds are kind of like petals on a flower, like 2 leaves overlapping, 2 balloons tied together. All right, so those are our different models, and then we're going to talk about those principal energy levels and how we get different spectral lines. Electrons are found in principal energy levels, so those are distances away from the nucleus, and you can tell how many principal energy levels by looking at the period number of the element. So let's take potassium, for example. Potassium's in period 4. He's going to have 4 principal energy levels. Let's look at your periodic table. Here's potassium. He's in period 4. His electron configuration down here, 2-8-8-1. So there's 1, 2, 3, 4 numbers. So let's write that example down in your notes. Potassium's electron configuration is 2-8-8-1. He has 4 principal energy levels. And what happens is these electrons, because remember they're moving in regions called orbitals, they're not stuck, they're not in fixed paths, they can move from one to the other. So if we give it some energy, if we heat it, or if we add electricity to it, they can jump to a higher level. So for example, as long as we have that same number of electrons, so here potassium has 19 electrons, he's neutral. As long as I keep 19 electrons, and I don't go over my maximum of 2 electrons in the first principal energy level, maximum of 8 in the second, 18 in the third, 32 in the fourth. As long as I don't go over those maximum numbers, then I can rearrange these electrons however I want. This, the way it is on the periodic table, has the least amount of energy. Electrons, like everything else in nature, are lazy. They try to go to the state of the least amount of energy. We say this is its ground state. When they've jumped to higher energy levels, we say that this would be the excited state for the electrons. They're absorbing energy when they jump to the excited state. Absorbing energy. So when you think of energy, one of the ones that they taught you the most about with energy was light energy in middle school. And when you absorb energy, when things look black, the reason you see the color black is because it has absorbed all of the colors of light. We don't see anything. The reason something looks white is because it's released or reflected all of the wavelengths of light, and you're seeing all of them. And so it's white, all of the colors mixed together. When they absorb energy and jump to a higher state, you get these absorption lines down here. See, they're black. Black. To us in lab, when it's absorbing the light, you don't see anything. What we do see are these emission lines. When they fall back to ground, because the excited state is unstable and the ground state is the stable one, when they fall back to ground, they release whatever light they absorbed. So if they absorbed in this wavelength of energy, they're going to release the energy in those same wavelengths, and then we see colored light. In lab class, you might see just a mixture of all of those colors together. So when we burn copper, it gives off a pretty green flame. If you use a prism or you use a machine called a spectrometer, the Spec 20, they're always using on CSI, you can actually split it apart and read the individual wavelengths. So right here they're showing you the jump from level 2 to level 3 absorbed this much energy, so the fall releases the same amount of energy. Equal but opposite, that's the conservation of energy, the law of conservation. The amounts of energy are measured in units that they call quanta or quantums. And it's just a measurement that the physicists use to see how much they absorb or release. And different changes give you different amounts of lines, different amounts of energy, different color wavelengths. Every element has its own unique signature of wavelengths. So if we look at some examples, and I know these examples, the writing is blurry. I really just want you to look at the lines. I'm sorry for the blurriness right now. Why do we care? Well, we use them to help identify elements. Down here, they have a set of target elements that might possibly be. These numbers down here are wavelengths of light in angstroms. And here are different stars. So star A and star B, and they're shining the light through. And what they do is they go down and they match them up. If you see these lines here, just like in Mercury, the lines, just like in Mercury, that match up, you can see that this star, since it has all of the lines that you see in Mercury in its spectrum, star B must have Mercury in it. And this is how they identify which elements there are in the star. They take the light from the star, shine it through a spectrometer, and get these wavelengths. The way that you would see this on the final, this is a very typical question on the final. It's really similar to DNA analysis in biology. What I want you to do, here's a mixture, and they might ask you which elements are in the mixture, and they give you some choices. So here they're giving you 3. What I want you to do is go through the lines and say, oh, there's a line that matches. Does it match any of these? Nope. Here's a line that matches, and actually match them up and see which ones they match with. And go through all of them. Way easier if you take a piece of paper and you follow along beside them. Now, if I had to guess which things were in my mixture, I would pick this one and this one. And I would ignore this one because not all of the wavelengths are there. There's only one, so that's not going to be it. It has to have all of the bands in it. Very, very typical short answer question on the final exam. I've seen it more than once. And this is just reminding you that this is what the electromagnetic spectrum looks like. So our Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And emission spectrums, you would see the light. This is when it falls from excited to ground. And we see light. This is when they move up from ground to excited. They absorb light, and we see nothing. In lab, you're going to see nothing at this point because it's absorbing the energy. It's not coming to our eye. We can't see it. It's really important that you memorize this movement, that you can describe the movement and when you see light. So the movement is electrons are in the ground state. They absorb energy, move to excited. A lot of times instead of move, they'll say jump. We see nothing. It's unstable, so they fall to ground. They fall back to ground state that they were in the first place. And that's when we see colored lights. Memorize that pattern and you're all set. They're not going to ask you for specific wavelengths. They're not going to ask you for specific movements. They're just going to maybe ask you to pick out which one is excited. Ground state are the ones that are on the table, and the excited states don't match the table. They're going to look different. And then that's it. All right, that's it for this lecture. More on electrons in Lecture C.